Hello friends, in last lecture we have defined analytic functions and we have seen one example of analytic function. If you recall, we have shown that this function is nowhere analytic. So let us just recall the definition of analytic function. The function f of z is said to be analytic at a point z0. The function is said to be analytic at some point z0 if there exists at least one neighborhood of z0. If we can find out at least one neighborhood of z0 such that f of z is differentiable at every point inside that neighborhood, and if the function is analytic at every point in the complex plane, it is known as entire function. So entire function means function which is analytic at every point in the complex plane, or we can say that the function which is analytic everywhere. The function which is analytic everywhere is known as entire function. So here we have to show that this function is entire. That means we have to show that this function is analytic at every point in the complex plane. So this function is already in this form u plus iv. If you compare this right hand side with u plus iv, suppose this is equal to u plus iv. Say this is u plus iv, then u is e raised to minus y into sin x and v is e raised to minus y into cos x. So to decide the analyticity, first we have to decide at which points the given function is differentiable, and for differentiability we will first decide that at which points Cauchy-Riemann equations are satisfied. So for that we have to find our partial derivatives of u and v. So u is e raised to minus y into sin x. So if we differentiate u with respect to x, we will consider y as constant. So therefore e raised to minus y is constant and derivative of sin x is cos x. Similarly, with respect to y, if we differentiate u with respect to y, then we consider x as constant. So sin x is constant and derivative of e raised to minus y is minus e raised to minus y. V is e raised to minus y into cos x, so del v by del x will be minus e raised to minus y into derivative of cos x is minus sin x. So minus minus will get plus, and derivative with respect to y is cos x constant and derivative of this e raised to minus y is minus e raised to minus y. So it will be plus here. Now we have to check whether ux and vy are equal. So here we can see ux and vy are equal at every point. Okay, because right hand side is same at every point, we can say that ux equal to vy is satisfied at every point in the complex plane. Similarly, second equation is uy equal to minus vx. So this is also we can see vx is e raised to minus y sin x. So if I put value of vx here, I will obtain uy equal to minus vx. So this equation is also satisfied at every point. That means both Cauchy-Riemann equations are satisfied at every point in the complex plane, and also these functions are continuous at every point in the complex plane, because we know that trigonometric functions sine and cosine are continuous everywhere, and exponential function is also continuous everywhere. Therefore we can write that ux, uy, vx, vy are continuous at every point z equal to order pair xy. So both the conditions for differentiability are satisfied. Therefore f of z is differentiable at every point, and if the function is differentiable at every point, it must be analytic at every point, because function is differentiable at every point. So if we consider any point in the complex plane, function will be differentiable in any neighborhood of that point. If I consider this point in the complex plane, then if I consider any neighborhood of this point, function is differentiable at every point in that neighborhood, because function is differentiable at every point. So if our function is differentiable at every point, we can directly say that function is analytic at every point in the complex plane. Therefore, given function is entire function. So in this way we can easily decide the analyticity of a given complex function. We may have more than one examples also. Suppose I consider this one. So that f of z equal to 2xy plus I into x square minus y square is nowhere analytic. So again we can compare this with u plus iv. Okay, first we check at which points CR equations are satisfied. So u is 2xy and v is x square minus y square. Del u by del x will be 2y constant, derivative of x is 1. Del u by del y is 2x constant, derivative of y is 1. Del v by del x is 2x and del v by del y is 0 minus 2y, that is minus 2y. So now we check at which points these two are equal. So ux and vy, okay, we have to concentrate on these two, ux and vy. So these two are equal if 2y equal to minus 2y, and if we take this 2y on left hand side, this is true if 4y equal to 0, but 4 is non-zero, so we can take 4 on this side. So 4 into y equal to 0 is possible if y is 0, because 4 is non-zero. So this equation is satisfied at all the points x, y in the complex plane for which y coordinate is 0. This equation is satisfied at all points whose y coordinate is 0, and these points are lying on x axis, because if we take any point on the x axis, then y component of that point is 0. So first equation is satisfied at all points on x axis. Okay, we can visualize in this way also. Suppose I consider this xy plane, then first equation is satisfied at every point on the x axis. Ux equal to vy is satisfied on x axis. X axis can be represented by the line y equal to 0. Similarly, we can check for second equation. For second equation, we have to concentrate on these two derivatives. So uy equal to minus vx if 2x equal to minus 2x. This means if 4x equal to 0, that is if x equal to 0, and the points for which x component is 0 are obviously on y axis. So second equation is satisfied at all the points on y axis. So the common point at which both equations are satisfied is 0 only, or origin. So we can say that both Cauchy-Riemann equations are satisfied at z equal to 0 only. That means function is not differentiable at every non-zero point, because CR equations are not satisfied at every non-zero point. So if z is non-zero, function is not differentiable. Now at z equal to 0, we have to check continuity condition. So obviously all the partial derivatives are polynomial functions and they are continuous at every point. Therefore they are continuous at z equal to 0 also. Therefore at z equal to 0 both the conditions are satisfied, and hence function is differentiable at z equal to 0 only, and function is not differentiable if z is non-zero, and the function which is not differentiable can never be analytic. So if z is non-zero, function is not analytic. Now at z equal to 0 function is differentiable, but for analyticity we have to find out neighborhood of 0 such that function is differentiable at every point in that neighborhood. But if we consider any neighborhood of 0, there are some points in that neighborhood which are different from 0, and function is not differentiable if z is non-zero. Therefore function is not analytic at z equal to 0 also. So hence function is nowhere analytic. Okay, and you can have this remark also: if function is differentiable at finite number of points, say z1, z2 up to zn, the function which is differentiable at only finite number of points is always nowhere analytic. It can never be analytic. The function which is differentiable at finite number of points only can never be analytic. So here function is differentiable at only one point, therefore function is nowhere analytic. Okay, here we have written that note: if a function f of z is differentiable at finite number of points only, then f of z is not analytic. Okay, we can visualize in this way also. Suppose we consider some function which is analytic at some finite number of points, say z1, z2 and z3. Suppose function f of z is analytic at 3 points only. The function f of z is differentiable at 3 points only, and it is not differentiable at every point which is different from these 3 points. Then for analyticity at z1, we have to find out at least one neighborhood of z1 such that function is differentiable at every point in that neighborhood, but it is not possible. If we consider the neighborhood which contains all the points, suppose I consider this type of neighborhood of z1 which contains z2 and z3 also, then also we are having some points, we are having infinite number of points such that function is not differentiable at those points, because function is differentiable at z2 and z3. So same logic applies for z2 and z3 also. So if function is differentiable at finite number of points only, then for those points we are not able to find out any neighborhood such that function is differentiable at every point in their neighborhood. Therefore function is nowhere analytic, even if it is differentiable at finite number of points. Next example: show that f of z equal to x square plus iy square is nowhere analytic. So if you can recall, we have shown that in earlier lectures on differentiability, we have shown that this function is differentiable at the points of the line y equal to x only. Or you can use Cauchy-Riemann equations and you can decide that this function is differentiable at the points which are on the line y equal to x. This is x axis, this is y axis, and this is the line y equal to x. This line is y equal to x. So in lecture on differentiability using Cauchy-Riemann equations, we have shown that this function is differentiable at all the points on this line. There are infinite number of points on the line, and we have shown that this function is differentiable at all the points on the line y equal to x. Now for analyticity, suppose I want to check analyticity at this point. Suppose this point is 2, 2 or 2 plus 2i. Then function is analytic at this point if we can find out some neighborhood of this point such that function is differentiable at every point in that neighborhood. Okay, the point 2 plus 2i. This point is on the line y equal to x, or we can write order pair 2, 2 also. This point is on the line y equal to x, and function is differentiable at this point. But if we consider any neighborhood of this point 2 plus 2i, then in that neighborhood there are infinite number of points which are not on the line, and the function is differentiable at all the points on the line only. So if we consider any point on the line, then there is no neighborhood of that point such that function is differentiable at every point in that neighborhood, because if we consider the neighborhood of any point on the line, then there are some points in that neighborhood which are not on the line. So if we apply this logic, then function is not differentiable in any neighborhood of any point on the line y equal to x. So there is no point on the line y equal to x such that function is differentiable in the neighborhood of that point. So therefore f of z is not differentiable in any neighborhood of any point on the line y equal to x. Okay, we are not able to find out any point on the line y equal to x such that function is differentiable in the neighborhood of that point. So therefore function is nowhere analytic. So these are some examples. I am not going into the details, but in this way you can decide whether given function is analytic or not using Cauchy-Riemann equations. So in the next lecture we will see some more problems on analytic functions. I hope you like this lecture. Thank you very much.